So in this notebook walkthrough, we're going to look at the probability fundamentals that are relevant to deep learning. So we start with some basic probabilities. It's essentially just the likelihood of the samples, right? The distribution. It's all about the distribution of the samples. So we have So we talk about how to set up the experiment to get the distribution, uh, like the experiment, the sample space, and all that. We start out with a simple example. If a casting a die, we're starting with two dies, and then all that. These are very basic probability concepts, right? That are not very interesting. But yeah, basically we just talk about like how you should be computing. How do you compute the rules? How do you compute the probabilities, right? And all that. These are not very important. I want to get ahead to conditional probability. So we're heading into the Bayesian rules realm, which is becoming relevant in machine learning and deep learning. So a conditional probability is essentially saying if something has happened as a pre-assumption or as a condition, precondition, or what we call a prior, what then is the probability of event A happens, right? If B already happened, what's the probability of A? So it's written as probability of A given B, right? So yeah, so this is essentially the Bayes rules, right? And this visualization tells you perfectly well. So yeah, like this is the prior. This the whole thing is the sample space, right? Uh, the colored ones and the grayed out ones. Right, but if we're talking about conditional probability, we are only interested in this subset, not the entire sample space. So given that we have a face card, what's the likelihood of that card being the king, right? So yeah, the formal formula for that is P A and B and divided by P of B, which kind of makes sense, right? If you go back to the illustration, the visualization is essentially um, just the samples uh, distribution in the entire sample space. Yeah. So conditional probability, and then naturally we'll go on to Bayes theorem, Bayes rules, right? So this is the Bayes theorem. It looks fancy, but it's honestly just a natural step from the above formula, from this formula, right? It's the same thing. If you move probability of B to the left-hand side, then you're essentially getting the same thing, getting the same thing, right? Yeah, like I talked about, like the prior, the posterior, and the evidence and all that. These are just fancy names. These are just fancy names. But yeah, essentially it's the same thing. So yeah, Bayes rules and whatnot. Now, Bayes rules is very important in deep learning. So this section talks about that. So there are a class of classifiers that are based on Bayes rules. They're called naive Bayes classifiers, right? And Bayesian neural nets and all that. Very, very important concept. random variables, they're not interesting. Next, I want to move on to entropy and randomness. So, this notebook was given in like very weird orders. The order of the cells are messed up. So it starts from the middle, and then at the top, it's really the last cells. So I have to go back and forth. So I want to talk about entropy. What is entropy? Entropy measures uncertainness. Sorry, uncertainty, right? So, if there are four labels, then if you're very certain, then you get zero entropy, meaning that the distribution is just one for one of the labels and zero for others. That's very concentrated, very certain model. You get maximum uncertainty when the probability are distributed evenly among all the labels, right? So when there are a total of four labels, the maximum entropy is 2. So how are entropy calculated? How is it defined? It is defined, let's see, again, so the notebook is is going in back order right now. Um, Yeah, I believe it's the formula for that is this, right? So you have the formula for entropy. Yes. So it's the log likelihood times the likelihood, and it's a negative one. So in this it gives a concrete example to illustrate a point. So let's say we have uh, sample size of 10, and six of those are ones and four are zeros. Now, naturally, if we want a model that works correctly for this distribution, would given a input would have a zero point 0.6 likelihood to predict it to be 1. So that conforms with the distribution of the original data samples. Right. So we start with a random or start with a different probabilities, different p-values from zero point 0.1 to zero point 0.9, right? But as like I said, the best model should have p-values of zero point 0.6, right? So here we're computing the cross entropies. It's essentially the same thing here. And when we plot it out, indeed, at zero point 0.6, we have the lowest cross entropy, meaning that when when p equals zero point 0.6, the model has a result that has like the least kind of uncertainty or the least difference from the true distribution. So a very important concept is when you minimize cross entropy, you're actually maximizing the log likelihood of the model. Yeah. So how is this connected to what we have discussed before, like back propagation, chain rules, gradient descent? Well, it's related to that when we use softmax as the final activation functions. Um, when we do that, we have we're kind of like using the cross entropy as the objective function, right? We want to minimize the entropy. So that is the end goal, and then that is the objective function. That is the loss function we want to minimize. So that's when gradient descent comes in, right? We want to minimize that, and we use gradient descent, and then we use back propagation to kind of go backward and optimize the weights. So that's how it's all connected. Yeah. So these are not. So one more interesting thing in this notebook is Gaussian distribution. Gaussian distribution is really a fancy name for normal distribution or binomial distribution. They're the same. Um, and what really matters is the mean, the standard deviation, or the variance. Once you have those parameters, you basically the shape of the distribution is fixed. You know the shape of the distribution. Yep. So yeah, that's pretty much all. So yeah, here it talks about the softmax, right? How it's related to deep learning. Now that we have all of these, yeah, that's pretty much all for the next notebook. Thanks for watching.